Okay, we're going to do another video where I use Geogebra for an algebraic application more than your classical geometry. This time, here's a problem I like to give my students when we're studying polynomials, and I'm going to use the text so that you can see on the screen. In the input bar, if you want to type text, just put it in quotation marks. I'm going to try to come up with a function where the x-intercepts. Its attempt to use the intersections and things confusing me on my typing there, but the x-intercepts, we're going to put those at the points a0, b0, and c0. You could do this with a numerical example, but I'm going to show you the sliders again. So I'm going to define sliders a, b, and c and try to come up with a function that has its x-intercepts at those points. So let me go ahead and define the sliders. So I did that in a previous video. You just use the slider tool, click on the screen. I'm going to go from -5 to 5 by 0.1. Let's move them around a little bit. Let's mix them up. Let's set a to -2, b to 1, and c to 3. Let's go ahead and plot the points now. a0, b0, and c0 on the x-axis. Let's change the colors and coordinate them. Let's make A be red. I had previously selected some colors, I'll use it there. And let's make this match. Let's leave B black and make C blue. So you just right click on the object properties and then you can change the color. And if you've picked a color, you can click on the recently selected color to make sure they match. So there we have 3 color-coded sliders and the corresponding points on the x-axis. So if I want a function to go through those, it just needs to have those things as factors. So let's let y equal x minus a times x minus b times x minus c. Hit enter, and we have our function. If we change the values of a or b or c, even if they converge onto one another, we see that our graph indeed always has the x-intercepts at a, b, and c. Let's try for the y-intercept. That's always tougher for students. Let's let the y-intercept be at the point 0d, which I'll have to define d. So let's add a 4th slider, d. And right now our y-intercept is somewhere around 3.5. Let's see if we can make it go through d. Well, the way to do that would be to look at, just for notational purposes here, I'm not going to enter this in, but you can, instead of just using what we did for f of x, you can use a times f of x. Actually, we've already used the letter a in our formula. Let's call it, how about m times x minus a times x minus b times x minus c. So that formula would still go through, for any m value, the x-intercepts a, b, and c, but I want it to go through a y-intercept and come out with a y value of d, and I would then plug in 0, so I'm just using the input bar to show you my computations. I plug in 0 and solve this thing. We'll get that m is going to be d. Let me write over here, m will wind up needing to be d divided by, there's 3 negatives, so there'll be 1 negative, a times b times c. Okay. So let's copy that. Actually, Geogebra, there's the one thing I wish you could do on Geogebra. It will not let you copy text from the command line. So let's remember that. We need to add the coefficient d divided by -a times b times c to get the y-intercept that we want. Okay. So let's clear all this out. Let's go up and right-click and edit this thing. Go to Object Properties, the Basic tab. Let's multiply this thing by d divided by parentheses -a times b times c. Add that to the graph. And there indeed we have it now going through the point. And let's add the point 0d. Let's make that green. How about a nice dark green? And let's change the slider to match. So there you have it. For any a, b, and c, and d that I set with the slider, we have a polynomial that goes through the x-intercepts at a, c, and b, and has a y-intercept at d, even if we change those values. So the power of dynamic geometry, I call this dynamic analytic geometry because we have the coordinates and the equations, but it's dynamic. If we change any of these numbers, it updates in all of the other representations.